Okay, so today we're going to discuss the first half of Chapter 11. So, Chapter 11 is the composition of solutions. So, what is a solution? We've kind of discussed this before, right? So, it's any homogeneous mixture at the molecular ionic scale. So, anything that is a homogeneous mixture, right? So, remember when we say homogeneous, we had a heterogeneous and homogeneous mixtures, right? And heterogeneous is what? Where they are different, right? So they don't mix together like Cheerios and milk. That would be a heterogeneous. And a homogeneous would be like salt water, right? Where the homogeneous is that everything's uniform, right? There's no difference in anything, in any of the two substances. Everything's one uniform substance. So a solution is a homogeneous mixture at the molecular ionic scale. So in a solution, the two parts that we have discussed before are a solute and a solvent. And remember, like I was saying, you put the lute, right? If you're a robber, where am I going to put my lute? Oh, in the vent. Right? In the vent. Put my lute in the vent. Put the lute in the vent. Right? So those two things, and once you put your lute in your vent, this now is a homogeneous mixture, and as long as it's a homogeneous mixture, it will be considered a solution. Okay, solubility. So, solubility, how readily or completely a solute dissolves in a solvent. So, a soluble ionic compound dissociates into ions when dissolved in water. So when it's soluble, we've kind of talked about this like electrolytes, right? When you have something that is able to easily disassociate, its ability to disassociate is going to tell you how soluble something is. So like when we were talking about precipitation reactions, right? And we said, oh, one of these products is going to be a solid and one is going to be aqueous. Well, what is aqueous? It means that these like little molecules, these little ions just like floating around in water, right? Just floating around, which means that that mixture is a soluble mixture, right? Because when we looked at our periodic table or solubility chart, it would say it was either soluble or insoluble. So if something is soluble, that means that it's able to disassociate completely and into its different ions and when it's dissolved in water. So that means it's soluble. So when it, for instance, when we did our reactions and one of the molecules was solid and the other was aqueous, that meant that one that was aqueous is a soluble mixture because it broke down into individual ions. And insoluble compounds remain mostly undissociated in their ionic structure, their crystalline structure. So when it's insoluble, like in our precipitation reactions, it's a solid, so it doesn't break down into a homogeneous mixture with the water, right? It just stays as like a solid of whatever that compound is. So insoluble means it can separate and dissociate, and then soluble means it separate, dissociate, and insoluble means that it cannot. It is insoluble. It's unable to dissolve. Just made that up. Or soluble, it's able to dissolve. Okay, so remember this chart, right? You guys just use this in your exam. So this is the rules to predict this solubility. So this is not a concept that's totally foreign, right? We talked about solubility before. So these are the things that are able to disassociate completely in a liquid. Or, for instance, like some of them, right? So all nitrates are able to disassociate. So if you had Na, right? So that would be something that would completely dissociate because all nitrates are soluble. But if you had, for instance, like the carbonates are insoluble. So if you have CO3, right? Mg, magnesium, CO3. that would be something that would be insoluble. So these MgCO3 carbonate is not going to dissociate. Okay, hold on 1 second. Close the window. All right. Okay. Okay, so now let's get into electrolytes. So we've discussed these things. So this whole topic is on kind of stuff that we've kind of discussed. It's just going into more detail. So it should be a short lecture. So electrolytes and non-electrolytes. So you have 3 different areas that kind of break up electrolytes, right? You have strong electrolytes, weak electrolytes, and non-electrolytes. So the strong electrolytes, a solute that dissociates completely into ions in an aqueous solution. So this would totally separate into individual ions, Na plus and Cl minus, right? That's an awful pen. Okay. Right, and so then a weak electrolyte is a solute that dissociates partially into an aqueous solution. So let's say if you had something that has hydrogen and H HO, and let's just say that there's like a Na or H NaCO3. Okay, I don't know. Or not Na, let's put magnesium. Mg. Okay. So something that would dissociate partially. So this hydrogen, right? That could be slightly dissociated from this compound, right? That might slightly separate when it's dissolved in water. But as we looked at earlier in the solubility table, magnesium and carbonate are not going to dissociate. So in this example, the hydrogen has maybe slightly separated, right? But this magnesium and carbonate has not. So therefore, that would be an example of a weak electrolyte because partial dissociation has happened. And the last one is a non-electrolyte, so a solute that does not dissociate into ions in the aqueous solution. So if it was just that magnesium, CO3, right? So this is an insoluble molecule, right? That's another way to say that. Because it does not, and it also is not an electrolyte, right? An electrolyte is when it dissociates into its ions completely, okay? So when it's non-electrolyte, it doesn't at all. It does not dissociate into its aqueous ion. So it would be something that is insoluble, like this Mg, magnesium carbonate. Okay, the solution process. How do substances dissolve to make a solution? So how does this process happen? So, as we discussed in the last lecture of intermolecular forces, right, there's going to be a force here in this same situation. So, and that force is called an ion dipole force. I wonder what this force is between an ion molecule, or an ion, and a molecule that has a dipole. So an attraction between an ion and a polar molecule, right? Yes. So when an ionic compound dissolves in water, ionic bonds in the solute break. Hydrogen bonds between water molecules break, and ion dipole forces form between the ions and water molecules. So when you're thinking of when these ionic compounds dissolve, so like sodium chloride, right? So when that dissolves, this when you have this sodium chloride, and you're putting that into this. Right? You're putting in this in here, putting your sodium chloride into the water. So what happens is that this ionic bond breaks, the ionic bond in the solute breaks. So this bond here between the sodium chloride break, right? And that's how we get the Na plus and Cl minus. But those are not ions, so now these are our electrolytes. So the ionic bond would break, and then the hydrogen bonds between the water molecules break. So these bonds here break. Okay, so now you have all these little molecules that are floating around of ions of water. And then, so what happens once these have separated and these have separated, and in here, you now will have an ion dipole force between the ions and the molecules formed. So these are our ions, the sodium chloride, right? And then these are our molecules. So what happens is that there's going to be some sort of connection that is happening between the sodium and the oxygens, or the hydrogens and chlorines, right? So it's not, and that's why it doesn't consider it as a chemical reaction, because there's just a force that is keeping these things together. So instead of these lines, because the lines are bonds, I'm going to draw a little line, several lines, because this is saying it's not a bond, it's just a force that is keeping these together, right? Just a little force that's keeping them together versus it being, there's a bond. So it's an ion dipole force. So this is between this molecule, there's an ion dipole force that's happening, okay? So hopefully that makes sense. So when you think of ion dipole, it's between an ion and then a molecule. So the heat of solution. The difference between the energy required for separation of the solid and the solvent and the energy released upon formation of the ion dipole interactions. So when we're thinking of how much does this solution, how much heat is either being taken in or broken, right, is basically how much heat is used to break these bonds and how much energy or heat energy is used to create the ion dipole. So energy from the breakage of the bonds of water and the ionic bond, and then the formation of the ion dipole forces. So that's the heat in the solution, is the amount of heat required to the separation of each of the solute and the solvent, and then how much energy is used to make the new forces between the ion and the dipole. Okay, so these are, once again, like I said, I keep saying, these are topics that we have talked about before, right? So exothermic. When you think of an exothermic solution, so what does exothermic mean? That the heat is what? Exiting the system, right? It's exothermic, it's exiting the system. So in this process, this is showing the breakage of like the solvent, solute, and of the formation of the new solution, right? So it's saying here, this is how much energy, so you have your solvent being aggregated and then it's separated, and then here's aggregated and it's separated. So this is kind of where you're starting, and then this is where you're going. So there's a certain amount of energy that is needed to go from here to here. So this is like E1, right? So you have this amount of energy to go from to break up your solvent. And your solvent is what? The water. So how much energy is needed to break those hydrogen-oxygen bonds? That's E1. And then the second energy, because you want to think of everything that's being involved in the solution. So all the molecules that are breaking in the solution, and they're from the solvent and the solute. So the solvent breaks up, that's one energy. Solute breaks up, that's another energy. So then the solution, the energy of the solution would be what? The added energies together would be the energy required to break bonds and intermolecular forces of the solute and the solvent, right? Because that's how much, or that's what the solution is made up of, solute and solvent. So, and then the last one, because you have your energy from the solvent and solute, which is the solution, and then the energy it takes to make that ion dipole force. So energy is then released from the formation of the solute-solute interactions, intermolecular actions. And then the energy released is greater than the energy required of the solution. So the solution is exothermic. So basically, how much energy that you needed to, how much energy is released, or yeah, how much energy, excuse me. So the energy released, which is the energy, is greater than the energy required. So the solution is exothermic. So the amount of energy that is needed to create this solution is less than the energy that's given off to break up the solution. So if you have, it takes more energy to break the solvent and the solute down, right? There's more energy to do this process and this process than it is for this process. Then you know that this is going to be exothermic, because this is how much, this is the energy released from the formation of these two, the formation of the ion dipole bond. So the energy released from the formation of the solute-solvent intermolecular attractions, that's that new ion dipole. And this is the energy that is required to take, to break the bonds of those. And then this is the energy that is released, right? So this is the initial energy, and this is the final energy. So this is how much it took to break the bond. So it added energy to break these bonds, and then it released that energy to make them. So this is how much energy it took to break them, but then to put them back together, it released way more energy in order to put them back together, to make that ion dipole force. So because the amount of energy that it took to recreate those bonds is releasing that energy. So here, this is a lot of energy, right, to break these bonds. So you're adding energy. So that's what this energy thing here is increased energy. So you're adding energy to break these bonds. So this is endothermic, this is endothermic. And then in order to make this final solution, which is the ion dipole, you're going to release that energy that you use to break these. And so the amount of energy that you're releasing to make this new solution is going to be greater. The amount of energy that you release is going to be greater than the energy that you needed to make the solution. So if that's true, then it's an exothermic process. So if the formation takes more energy than the, dissolution or breakdown, then that's exothermic. So hopefully that made sense. Endothermic would be the opposite. So here you have your energy, and you're going to have your endothermic, which is going to indoors, right? So the system is acquiring heat. So let's now look at this from the endothermic section. So the exothermic was the solution, the solvent. There's a lot of energy in the solvent and the solute, but it took more energy to release more energy to create the new solution, right? So this is added energy to break these more, and then more energy more energy was given off in order to create the ion dipole. So that was what the last one was, exothermic. Here we have energy for the solvent that's needed to break the solvent. So we're adding energy, right? Adding energy to make the solvent, adding energy to make a solute. So then you can add those together, and that's going to be the total amount of energy in the solution from each one, right? So when you have this is like your initial, and then your final will be here, because, so if we're now up here, because this is the amount of energy total that is needed to make the solution. This is how much energy we use in order to create the solution. But then now that these have broken up, so now we're here, it's going to start making that ion dipole formation. And when it starts making that ion dipole formation, that energy that it added, so it's like energy came in, energy. So all this energy, right? So all this energy. So, but then when it makes the formation, the energy releases. So as it's releasing this energy, the amount of energy released in the ion dipole formation is going to be less than the energy needed to create the dissolution of the compounds, of the water and the ionic compounds. So this energy here is going to be, the energy added is going to be higher than the energy released. So therefore, the process is endothermic, because you need more energy added to the system to break up the molecules than you need to release to make the formation of ion dipole. Okay, so solution process for nonpolar interactions. Okay, London dispersion forces hold together the molecules of solid iodine, too, and liquid solvent, carbon tetrachloride. When a solution of I2 and ClCl4 form, new London dispersion forces form. So, nonpolar interactions. So how are these nonpolar and nonpolar compounds coming together? We've talked about how we have polar and polar, right, which is a dipole-dipole. We've talked about how those are coming together through the dipole-dipole, right? But how are the nonpolar? Well, the London dispersion forces is what holds these pieces together. So when the solution of I2 and CL4 form, a new London dispersion form. So the London dispersion is the process for which these interactions happen. Okay, entropy and solution. So we've heard of enthalpy, right? And enthalpy is heat. Okay, and entropy, which is going to be a measure of the tendency of matter to become disordered. So you will see this sometimes as a delta S, right? And so that's saying the change, they also kind of say the change in randomness. So like the spontaneity of it. So matter spontaneously changes from one state of order to a state of randomness unless energy changes oppose it. Solutions form because the makeup of the solution naturally tends towards disorganization. So entropy is just how much that piece of matter is going to become disordered. So naturally, things are in disordered. So, for instance, if someone says, like, if you have your stuff everywhere in your place and your place is a little messy, you're like, actually, the thing is that I'm not trying to work against the universe because things are naturally in disorder. So, if I create order, then the natural tendency of my room is going to want to be disordered. So, what's the point of cleaning when disorder is inevitable? I mean, not really, but just saying. So if anyone ever says like you need to clean your room, it's like actually I'm going to invoke the concept of entropy, which is the measure of randomness, and that's the measure of degree of which things tend to be always in disorder. Okay, so these solutions will naturally towards disorganization. All right, so now let's talk about factors that affect solubility. What determines whether one substance will dissolve in another? So there's three factors that will determine if one determine whether one substance will dissolve in another, and that is the effect of solubility, the structure, temperature, and pressure. So it's basically like how soluble something is based off of the structure of the solution, right? So what's there, kind of what we were talking about, like depending on what kind of compound it is, it can, separate easily. The temperature, if you increase the temperature, that can increase solubility because you could be breaking bonds. And then pressure, which is going to actually create, if you create pressure, you're going to separate possible molecules that way, and which will possibly create more solubility. So you can put pressure on something to create the solubility, increase the temperature to break the bonds, or the structure itself can be soluble and non-soluble. Okay, so 1, structure. Solubility of water, solubility of solid in the energy released by the solvation process must compensate for all the energy required to break up both forces at work, both within the solute and solvent. So when you're thinking about this, like if something is soluble, so you want to think that energy released by the solvation process, has to compensate for the work that the energy that's used for this solute and solvent, right? So what is the energy released in this solvation? So when you think of the solvation, thinking about of when that formation of the ion dipole is happening, right? So when the ion dipole is forming, you're going to be releasing heat. So the energy that's released in this ion dipole force creation must be compensated for all the energy required to break it up. So just like how we were talking about the endothermic and exothermic process, it must account for, solubility is going to involve the energy that it takes to break up those bonds, and then the energy, as well as the energy that it takes to make that new force, right? And then you also always want to take into account the entropy factor into the randomness. So solubility of a liquid depends largely on the polarity of the solute and solvent. So if it's a solid, it's more about the energy, right? Which makes sense because if a solid is, a solid is obviously solid. So it's going to have, you're definitely going to need energy in order to break up those bonds, right? So that they can be electrolytes, right, into individual ions. And then that's going to be released once those forces are created. So that's how that's the solubility of the solid. And then the solubility of a liquid in a liquid is based off of the polarity, right? So because it doesn't need to figure out a way to create a homogeneous mixture because it's already kind of, they're both liquids, so they can both like kind of be near each other. But whether or not those mix together is going to depend on the polarity. So if you have something that is polar, right? These dipoles, you have a dipole-dipole. But if you have something that is like polar, non-polar, like oil and water are opposites, those are not going to combine. So hopefully this is um, making sense. All right. So let me keep going. So now let's get into likes dissolve likes. So when the polarity of the solvent is similar to the polarity of the solute will dissolve the solute. So likes dissolve likes. So if it's the same, they're gonna like to each other and like mesh together, right? So when you have the so when you have polar solvents dissolve polar or ionic solvents, nonpolar solvents dissolve nonpolar solutes. So if you have an ionic solution, right, you're going to have your solvent is going to be soluble, and it's going to be polar, which is going to be soluble, and the nonpolar version is going to be insoluble. And then for the polar, it's going to be soluble for the polar, and nonpolar is going to be insoluble. And then for the nonpolar, it's going to be insoluble for the polar, and for soluble, it's going to be, for nonpolar, it's going to be soluble. Because what are we saying here? That the likes dissolve likes. So polar solvents dissolve polar solutes. Here's your solute, here's your solvent. So if we are thinking about this in when you have your ionic substance, right, you're going to have like a polar molecule. So you're going to have things that are going to be pooling. There's going to be pools. And so that's going to be soluble, right? Because it's kind of like ionic can be that. And then it's going to be insoluble because it's not polar. It's non-polar. And then polar, so you have your solute is polar and your solvent is polar, then you're going to be soluble, right? Just like if you're nonpolar, your solute is nonpolar, and your solvent is nonpolar, then it's going to be soluble. And then if it's opposite, so if it's polar and nonpolar, then it's insoluble. And then if it's nonpolar and polar, it's insoluble. So just remember that likes dissolve likes. So if you have a polar solvent, then your solute must be also polar, and vice versa. Okay, miscibilities. So, if two liquids can be mixed in any portion to give a homogeneous solution, then they are miscible with each other. So this is generally like liquid. So miscible, right? So this is carbon. These are liquids that are adding to this other liquid. And so basically it's saying, is this solution going to be homogeneous or is it not going to be? And when something is going to be homogeneous, that means that there was a like that dissolved like, right? So this would be like a nonpolar molecule with a nonpolar molecule, or a polar with a polar, right? And so when these two liquids mix together, they call them miscible. So they're mixable. They're miscible, mixable, 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 miscible. Just to help you remember, miscible. It's called miscible, but I think of like it's mixable, so it's miscible. Immiscible means that it does not mix, right? So like oil and water. So oil and water are going to be things that are not like. So your oil is going to be nonpolar and your water is polar. So that's why they don't mix. It's immiscible because they are not the same. Okay? Okay, so here's a breakdown of kind of that. Or another breakdown of something that is like water, the water soluble and fat soluble. So here, this is vitamin A. This is mostly nonpolar. This is vitamin C. This is mostly polar. So remember that when you think of something being soluble or not soluble, it's based off of the solvent and solute being in the same kind of polarity. So are they both polar or are they both nonpolar? And if they're both polar, then they will be soluble. Or nonpolar, they'll be soluble. But if they're opposites, the opposite is true. So this vitamin A is nonpolar, and the fat is going to be nonpolar, so that's why this is fat soluble. Okay, vitamin A. So this molecule is polar, vitamin C. So vitamin C is going to be able to dissolve in water, which means soluble, because it is polar. And then a fat molecule, which is also triglyceride, which you'll learn a lot in biology if you were organic. And this molecule is mostly nonpolar. So if this molecule is mostly nonpolar, right, would it be water soluble or fat soluble? Well, what is water? Is water polar or nonpolar? Water is polar. And like I said, this fat is nonpolar. So if our molecule is mostly nonpolar, then it's going to be fat soluble, and it would be insoluble to water, right? Okay, hopefully that makes sense. Okay, temperature affects the solubility of substances in water. Most ionic solids are more soluble in water at higher temperatures. Which makes sense, right? So the more heat and energy that you have to break up these tight bonds, the more soluble that they would be, because they're able to disassociate into their individual ions, and then create the ion dipole force. Gases are less soluble as temperatures increase. So with the solubilities of water, right, it's going to be higher because, well, when you have these solids, are they moving around as much? No, right? These solids are kind of going to break up into like these smaller, maybe little solids, and create this ion dipole force. But because they're solid, right, they're dense and they're not moving, so they're going to be able to be more soluble because they're able to separate and be these little steel molecules that are able to just connect and create these ion dipole forces with water. Unlike gases, right? What are going on with gases? There's like pew, pew, pew. I'm everywhere. I'm a gas. Just moving around, right? So with gases, they're less soluble as temperature rises. Because what happens to the gas when the temperature rises? They're like everywhere. So before they're like hanging out. Then we increase the temperature, turn that up, and then they're like, right, moving all over the place. So that's not going to create an environment that's going to allow solubility to happen as greatly. So as you increase the temperature, the solubility is going to decrease. Okay? Okay. Oops. So, solubility, pressure. The solubility of a gas in a liquid is directly proportional to the pressure of the gas above the liquid. So we actually talked about this before, right? We talked about this in the last lecture where I was discussing boiling. And so boiling happens when there's an equilibrium of pressure of air pressure to the water vapor, right? So as the boiling happens because of the pressure that's happening from the outside, and the inside is kind of boiling over. Not that way, boiling over. So pressure, the solubility of the gas in the liquid is directly proportional to the pressure of the gas above the liquid. An increase in the pressure results in an increase of solubility of the gas. Affects gases, but not liquids or solids. So this is, the pressure here is dealing with the gas. So gases, right, are all spread out. They're all spread out. But if you put pressure on that container, right, that decreases the amount of space between the particles, which therefore increases the concentration in that small space of those molecules, which therefore will allow for a higher solubility content in that solution, because you're able to create more connections between the gas particles and the solvent, right? So an example of that would be soda. So that's the whole point of soda. So when you open a soda can, right? Like what happens? You open the soda can, and you hear it, psh, right? That's that carbon dioxide leaving. So what did they do in order to do that? They put pressure. They created this liquid, and they put pressure on the top of this liquid, right? They put the gas in here and then put added pressure, which is the cap, right? So they condensed all of this carbon dioxide into this. So there's pressure with this cap on here, and there's lots of CO2 that's within this whole soda, right? So you're able to condense all of the CO2 so that it can be soluble within the solution. So, but when you release the pressure, what happens? That's when you hear the psh, right? And some of that CO2 begins to leave. And over time, what happens to your soda? It becomes flat, right? Before it's carbonated, but then over time it becomes flat because we got rid of the pressure that was concentrating that carbon dioxide. So once you got rid of that pressure, now those carbon dioxide molecules that don't have space to move around are able to slowly leave the soda, which is why it becomes flat. So the concept of the pressure is that when you're adding pressure, it's going to increase solubility, right? So when you're adding pressure, you have this much space and these gas molecules are moving around in this space. Then you condense that space, and now the gas particles are kind of like this, right? So now you're able to create solubility in something for those to have the ion-dipole connections due to the pressure that you added. Okay, so just think of that every time that you open a soda, you're releasing the pressure, you're releasing the pressure of the soda, and the pressure was there to create solubility between the carbon dioxide and the soda solution, like whether that be Coke or Pepsi or Sprite, right? Like the Sprite would be your solvent, and then the carbon dioxide would be the solute. And so the solute can only dissolve in the solvent if there's pressure that's put on it by adding a cap or, right, sealing things. And then once that's open, then that pressure releases, and then that carbon dioxide that was soluble or was, in the solution is now leaving the solution because it's moving around. Okay. All right. So, like I said, that was a very short lecture. So that is all for now, and I will see you guys tomorrow.